Dore. Uh, Good morning, everyone. Welcome to the marathon session on power system. Okay, so I'm Giri, faculty of Home Institute for Power System subject. Okay, so in today's marathon session, so I'm going to discuss, some important formulas and the background concepts and some numerical examples, okay, to get the the clear understanding of the concepts. So that is what the today's agenda. Okay, so you know that in our the home institute we divided this power system course into three parts as per our gate syllabus only. PS1 that deals with the transmission and distribution part, PS2 deals with the analysis part, and PS3 deals with the three topics: economic load dispatch, load frequency control, and the power system protection. Okay, so quickly cover all these topics, and also we are going to discuss some numerical questions. Okay, so that's what we are going to do in today's session. So let's see the list of topics we are going to cover here. All right, so the first topic, as I mentioned, the PS1. So the first topic is PS1, which deals with the transmission and distribution part, right? So the topics we are going to cover here: number one, basics we are going to cover; number two, no, the line parameter calculation; then wave traveling; voltage control; or factor correction; insulators and cables. Okay, I hope my voice is clear, right? Yeah, insulators and cables. Cables, and the last topic is distribution system. So the last topic, distribution system. So these are the topics we are going to see as a part of our PS1 course. Once this PS1 course is completed, okay, so then we'll see what are the topics we are going to cover in PS2. Okay, now quickly I will explain what are the things which are very important in the basics. Okay, so we'll start with that. Yeah, so now let's say when it comes to the basics of power system, the two things you should know in basics part quickly. Number one, star connection and delta connection. I'm going to write the relations because we are going to use what so frequently, these relations. Okay, so the first one is what? Star connection. Star connection, right? There may be a line voltage and phase voltage, and line current and phase current. So what is the relation between them? The line voltage is equal to what? Root 3 times phase voltage. Because so throughout the electrical engineering, we are going to use these relations so frequently. Okay, so this is the first thing. I feel this is the first thing one should learn. So the relation between line and what? Phase quantities. Line voltage equal to root 3 times phase voltage at an angle 30 degrees. And the phase voltage equal to what? Line voltage by root 3 at an angle minus 30 degrees. And the line current equal to what? The phase current. Okay, so this is for what? A star connection. If you have a star connection, quickly write. Okay, there is a line voltage measured between what? Two lines, and the voltage across the impedance is called what? Phase voltage. Now this is the relation between line and phase quantities. Current monitored at the line terminal is called line current. Current flowing through the every phase impedance is called what? Phase current. The line current and phase currents are what? Same, both in magnitude and what? A phase angle. Okay, clear? I hope this is clear. Now let me write the delta connection now. Okay, quickly we'll move on to the delta connection. So when it comes to the delta connection, so let me draw the delta connected load. Yes, the current flowing through the phase impedance is called phase current. The current monitored at the line terminal is called what? Line current. Okay, line and phase currents are not same. The voltage across the impedance is called phase voltage. Voltage across this impedance is called phase voltage, and the voltage monitored between any two lines is called line voltage. Now tell me, the line voltage and phase voltage are same here? Yes, because voltage across the impedance is what? The phase voltage. So that's why I'm saying the phase voltage and line voltage are what? Are always same. Okay, so let me write quickly. The line voltage equal to what? Phase voltage. The line current is equal to what? Root 3 times phase current at an angle minus 30. But the phase current equal to what? Line current by root 3 at an angle plus 30 degrees. Okay, clear? Okay, this is 30 degrees. All right, so these are the two important connections. And throughout the power system, if it is a three-phase system, only these two connections. Complete power system is three-phase, you know that. Okay, yeah, we have a single phase two-wire system also there. That is for what? Secondary distribution only. But when it comes to this basics part, see, the entire power system, three-phase system, star or what? Delta. Only these two things. Okay, nothing else. Right, sir? So now, if you see one by one the equipment, how they are connected. Okay, so let's see the power system equipment, how they are connected. Okay, and why they are connected like that also. So power system equipments, if you see, okay, components of power system, how they are connected. Number one, generator. Believe me, generator, synchronous generator in power system is always star connected and the neutral is grounded. There are so many the confusions about why it is star and why it is delta. Please believe me, why we go for star connection is due to the availability of neutral. Okay, this is a commonly asking question, especially in the interviews, especially in the competitive exams also. So why the generator is preferred with star connection means due to the availability of neutral, earth fault protection is simple. Okay, make this point. Due to the availability of neutral, earth fault protection is simple. That's why generator is always preferred with star connection. Okay. Oh, there was a power cut here, so please be with me. Okay, so and we will start the session once the power is came. All right. So I think you can able to listen my voice, right? Okay. Uh, Thanks to the electricity board people. Right. We got the power now. Okay. Now just hold on. Yeah, generator is always preferred with a star connection and the neutral is grounded. Again, I'm saying why the generator is preferred with star connection means due to the availability of neutral. Next, when it comes to the transformer means what? The primary might be star or delta. Yes, secondary will be what? Either delta or what? Star. Okay, clear? So we'll start now. Just hold on. Okay. So all right. Yeah. So the components, basic components, as I mentioned, the number one is what? Generator. Already told you the generator is preferred with what? Star connection, and the neutral is what? Solidly grounded. The reason is due to the availability of neutral, earth fault protection is simple. Now, when it comes to the transformer, quickly we'll see transformer. Okay. What about transformer? Transformer means, yeah, generally I'm showing here. It might be a star delta transformer. It might be a star delta transformer. Star point always, grounded in power system. This is a basic thing we do. It is a star delta transformer. Generally preferred for what? Step up applications. Sorry, it's a step down application. Step up application. But one, the violation of rule here. That is what? DTR, distribution transformer. DTR means what? It's 11 kV by 415 volts transformer. It is a step down transformer, but secondary is always preferred with what? Star connection, because the secondary side single phase consumers are connected. So to supply the single phase consumers, so it is always preferred with what? Delta star connection, because we need a 3-phase 4-wire system. Okay, then only the single phase consumers are connected. If it is a 4-wire na, or YB and neutral, then the consumers are connected. Some consumers are connected between what? R2 neutral, Y2 neutral, and what? B2 neutral. So these are what I'm saying, consumers is a neutral wire. So then approximately voltage is what here? 230 volts. Okay, some consumers are connected between what? R2 neutral, some consumers are connected between what? Y2 neutral, some consumers are connected between what? B2 neutral. So such that we need a neutral wire. We have to run the neutral wire. If you have a neutral wire, then only we can do that. That's why. So DTR is a step down transformer. Step down means star delta is shown, but better to go with what? Delta star here. Except DTR, everywhere we follow the rule. Step up applications, we use what? Delta star, and step down applications, we use what? Star delta. Okay, I hope this is clear for you. Chalo, right, sir. Now, the next important thing is transmission line. Now, transmission line is always star connected. Transmission line is always star connected. By default, truly speaking, it is neither star connected nor delta connected, because 3 lines are YB and this is the ground. So it is neither star connected nor delta connected, but for analysis purpose we use what? Star connections principle. For transmission line, yes, the line voltage equal to what? Root 3 times phase voltage at an angle plus 30 degrees. The phase voltage equal to what? Line voltage by root 3 at an angle what? Minus 30 degrees. Line current equal to what? Phase current. Okay, so that's for what? Transmission lines. Okay, so these are one basic things everybody know. Okay, so generator connection, transformer connection, and transmission line connection. Again, I'm saying transmission line is neither connected in star nor connected in delta, but for analysis purpose we use what? Star connection principle. Okay, so irrespective of star connection and delta connection, some important formulas which are very important to know. Next, that is what? Complex power. Everywhere we use this is a power. Complex power will give you the complete information about what? The active power, reactive power, apparent power, power factor angle. So it might be star connection, delta connection, everywhere it is valid. Blindly follow this. Okay, so there will be a gate question directly or indirectly on the complex power, believe me. Okay, so that's why be careful. Complex power means what? Always use the formula S equal to S bar, I will say, because it is a complex power, it is a complex number having a real part and what? Imaginary part. Okay, so a complex power means don't use root 3 VLIL. Don't believe line voltage, line current. Always phase voltage and phase current. Remember this. Always phase voltage and phase current. Okay, so 3 times V phase bar. Why I'm saying bar? Because it has a magnitude as well as phase angle. Generally, great electrical engineers neglect the phase angle. Okay, so they will write everything is in the magnitude form. That's why you please be careful. So you are dealing with the the phasors. You have a magnitude and phase angle, so be careful. Otherwise, you end up with wrong answers. Okay, believe me. So 3 into V phase, I phase, and a conjugate. Yes, the conjugate also requires what? Apparent power. Okay, so and the phase angle is what now? Power factor angle. And be careful, if this phase angle you got positive finally, then it is what? Lagging power factor. Believe me, lagging power factor. Don't question yourself. Positive means leading, negative means lagging, but it's not true for everything. It is okay. I'm talking about what? Complex power. I'm not talking about current angle here. I'm talking about what? Complex power angle, which is positive, believe, lagging power factor, which is negative, leading power factor. Okay, so always follow this. Lagging power factor and minus means what? Leading power factor. Okay, so believe this formula. It's very important. Okay, I'm going to solve one question for you so that you will get a more clarity on this. Complex power give you complete information. It gives you what? The active power, it gives you reactive power, it gives you apparent power, it gives you power factor. Power factor means what? Cos of this angle is the power factor. If you got positive angle, yes, you write what? Power factor is so and so lagging. If you got negative angle, write power factor cos phi, so and so leading. Yes or not? Okay. So that's how I'm saying. So yeah, let me write. So the real part is here, active power, imaginary part is what here, reactive power. I don't want to write the active power formula, reactive power formula. I am not going to believe them. I'm just going to believe only one formula, that is what complex power, because that gives the complete information. Even I'm asking to calculate for active power, even I'm asking to calculate for reactive power, I will always do it what? Complex power. Okay, clear? Understand? So I'm going to solve the problem. So that one more thing before concluding. So the impedance, no matter it might be star connection or delta connection, it has some impedance. Now, impedance means what? Per phase. Star connection, what is impedance? Delta connection, what is impedance? It might be star connection, it might be delta connection. Impedance is always per phase quantity. Divide phase voltage with phase current, you get the impedance. Okay, always remember impedance equal to what? V phase by what? I phase. So that is nothing but what? Impedance. Phase voltage by phase current is called always impedance. Okay, but what will change here is, for example, if impedance is given, directly how to calculate the complex power? Maybe it's a star connection impedance or delta connection impedance is given. How to calculate the complex power? Suppose if it is a star connection. Okay, here the things will change. What is the complex power of star connection? You can use 3 into V phase I phase conjugate formula. It might be star or delta. Let me write here first. 3 into V phase I phase conjugate. No problem. But you can also use like this. What? Magnitude of the line voltage square. Directly we get this. You have to proceed with this. I phase equal to what? V phase by Z. Yes or not? You have to write V phase by Z. Then V phase by Z and V phase, equal to what? V line by root 3. So once you do some calculation, so finally we get this. VL square by what? Z conjugate. Believe this. Z conjugate. VL square by Z conjugate. Yes, there is a gate question on this also. On this formula, there is a gate question. Okay. VL square by Z conjugate. Okay. So believe me. But if it is a delta, okay. So what is the complex power? Yes, in this real part is active power. Again, same thing I can write. Yes, same relations are valid again. P plus JQ. But you can use this formula because maybe star connected load impedance is given. Maybe a question is given like this. A 440 volts 3-phase star connected load has an impedance of 2 plus J2. Calculate the complex power. Calculate the active power. Calculate the reactive power. Calculate the power factor. This is how the question can be given. Group of questions. I'm going to solve some questions for you on the basics. Okay. So that we have a clarity. Okay. So it's valid not only for what? Power system. It's valid everywhere. It's valid in what? 3-phase system. It's valid in what? Your machines also. Okay. Clear? So that's why I'm saying these basics are very, very important. Yeah. When it comes to the delta connection, again, same formula you can use. 3 into V phase I phase conjugate formula, you can use it. But what I'm saying is, for a delta connection, if the impedance per phase is given, even if it is a star connection or delta connection, impedance per phase is given to you. So if the impedance per phase is given, then what I will write here is 3 times. 3 will come. VL square by Z conjugate. You might have studied in electrical machines also. The power in delta is what? 3 times the power in star. That's why sometimes, maybe for induction motor, while starting it is connected in star to reduce the starting current, but while running it is connected in delta to generate what? More power. Yes or not? Clear? So anyway, that's a different story, because see, for same line voltage you talk about here, it is VL square by Z conjugate. What about here? 3 into VL square by Z conjugate. Okay, just have a look at these formulas. They are very powerful formulas, very important formulas, believe me. Okay. There is no direction of convention for leading angle or lagging angle. Only one thing you need to see. If it is a load, current should be coming into the load. If it is a generator, current should be coming out of the generator. That's it. Except that, nothing else. Okay. I want to give a clarity on what? Convention. See, all these formulas valid for what? Both generator and load. Believe me. Generator valid. Load also valid. But what makes the difference between generator and load? Only one thing. That is what? If it is a generator, okay, you are saying this current I now. What is this current I? Okay, I phase. But what is this I phase? Current coming out of the generator, but not current coming into the generator. That is the only convention you have to follow. Okay. Generator means what? Let me write here. Generator means source, generator, source convention. Okay, that current what I am talking is what? It is out of the generator. Load means whatever may be the load. It might be synchronous motor, it might be induction motor, it might be resistive load, RL load, RC load, capacitor, inductor, whatever it may be, you take it. When you are talking about these formulas, when you are defining the power factor angle, positive means lagging, negative means leading. This is you need to apply by seeing the current which is into the load, source out of the load. There is no need to remember here. Source means it will deliver the current. Think like that. Load means it will take the current. Okay, clear, sir? If it is a load now, then what? You have to see like this. The current is what? Coming in. Okay, except that there is nothing else you need to consider. Except that nothing else you need to consider. Are you clockwise or anti-clockwise, lagging or leading? You forget about this. Okay, I'm going to explain that in the three-phase circuits. I'm going to take one more session, so I'm going to explain that. No need to worry. Okay, white child underscore 07. Nice. Chalo. So I hope this is clear. So I'm going to explain one question here so that you will get more clarity on this. Okay, chalo. Okay, this is a question. The load impedance is what? 10 plus J 17.32 ohms. It is supplied from 415 volts, three phase, 50H mains. So by seeing this question, one can understand that what? Supply voltage is what? 415 volts. Remember, rated voltage is always line voltage. Rated voltage is always what? Line voltage. Okay. So this 415 volts is nothing but what? It's a line voltage. It's a line voltage. Yes. The magnitude of the line voltage. It's not the phase angle given. Magnitude of the line voltage is given. Okay. How much it is? 415 volts. But when you want to proceed for anything, we need to define the phase voltage now. How to define the phase voltage? Phase voltage means always believe. Always you need to write like this. Magnitude of the line voltage only it will be given. Sometimes it will be given like 11 kV 3 phase 58 generator. 11 kV 3 phase 58 generator. What is that 11 kV? Line voltage. That 11 kV is the line voltage. What about the phase voltage? That 11 kV is the line voltage magnitude, no phase angle. Okay. So line voltage magnitude is this. What about the phase voltage? Phase voltage means what? This 415 by what? Root 3. Line voltage by root 3. But I will take the phase voltage only reference. Take phase voltage only reference always. Okay. Then only things become what? Simple for you. Okay, you can take line voltage reference and you can proceed. But by default, even it is not mentioned, phase voltage only reference. But which phase voltage is reference? Always R phase voltage is reference. If it is not given means, by default, this is what you need to take. R phase voltage, first phase voltage. Okay, if you follow RYB convention. If you follow A, B, C convention, A phase voltage is what? Reference. Okay, please, okay, follow this. It's always important. Okay, 415 volts by root 3 at an angle 0. Yes, phase voltage is reference. Okay, you calculate the phase current. Okay, you can solve like that. What about phase current? Phase current is how much now? What is phase current? So, V phase by always. This formula is valid with respect to phase. You remember, na? Z equal to V phase by I phase. Z equal to V phase by I phase. I phase equal to V phase by Z. But don't apply this formula, sir, for line. Some people will say that line current equal to line voltage by Z. That is blender, my dear. You can't calculate the line quantities directly. Calculate the phase quantities. Later you define what? Line quantities. There is nowhere written line voltage equal to line current equal to line voltage by line impedance. Line impedance has no meaning. Impedance is always per phase quantity. Impedance always per phase quantity. Believe this. Okay, V phase by Z. Okay, clear? Don't apply I line equal to V line by Z. Maybe sometimes in the question you'll ask to calculate what is the line current, what is the magnitude of the line current. Otherwise, sometimes the question might be given an ammeter is connected in the line terminal. What is the reading of the ammeter? Reading of the ammeter is always magnitude of the current. Yes or not? Okay, let's calculate always phase current. Later you define what? Line current. Okay, now tell me what is phase current? In this question, we are going to define everything. We are going to calculate the current, complex power, active power, reactive power, power factor, angle, power factor, everything we are going to calculate. Okay, so I just define line voltage, magnitude. Suppose if I want to write what is a line voltage here, since it is a star connection, line voltage magnitude is 450 volts, but if you want to write in phase angle form, nothing wrong to write like this. 415 at an angle what? 30 degrees volts. Sorry. Okay. Yeah. 30 degrees. 415 at an angle what? 30 degrees. Okay. Maybe you ask a question. Why only you are taking phase voltage difference? That is the standard, Rabbi. You have to take it. Always phase voltage difference. Now redefine the line voltage. But you may ask a question. Line voltage given in the problem now? Yes, that is given only magnitude now, but not phase angle. Okay. Careful about this. Chalo. 415 at an angle what? Plus 30 degrees volts. So if this is clear for you. Now, let's see. Yeah, phase current we are going to define V phase by Z. Okay, when you are calculating V phase by Z. Yes, one more thing when you are dealing with the complex numbers. When you are dealing with the complex number, remember one thing. Okay, so when you are doing multiplication and division, do it in polar form. Multiplication and division, do it in polar form. But when you are doing addition and subtraction, do it in what? Rectangular form. Rectangular form means what? X plus jy. Polar form means what? Mod x at an angle theta. Yes or not? You know that conversion, rectangular to polar, polar to rectangular. Oh, one should know about this. Then only things become what? Simple. Chalo. So how to convert this impedance to what? Z equal to what now? 10 plus j 17.32 now. What is its magnitude? Under root of 10 square plus 17.32 square 400. Yes, it's 20. Magnitude is 20. And what is the phase angle? Theta. Theta is the phase angle. Tan inverse imaginary part by real part. 17.32 by what? 10. So 1.732 root 3. Tan inverse root 3. How much? 60 degrees. Yes or not? Yeah, 60 degrees. Now I'm going to substitute in polar form. Okay. So 415 by root 3 at an angle what? 0 degrees. Divide with what? 20 at an angle what? 60 degrees. Now when you are doing now magnitudes, you directly divide. Okay. How to write this? Simple way. 415 by 20 root 3 is the magnitude. And what about the phase angle? 0 in the numerator, denominator is 60. So it will become what? Minus 60. Yes or not? Okay. Even you draw the phasor diagram for this. This is the phase voltage reference. Now, phase voltage reference. Na? Phase voltage what? 0 angle. What about the phase current? Lags the phase voltage by what? 60 degrees. Yes, it is a lagging power factor. Now again I am going to prove this. Again I am going to prove this from where? From complex power. Yes, lagging power factor. Current lags the voltage. Current angle is minus. Voltage angle is what? 0. Now you can say it is a lagging power factor. There is nothing wrong. Okay, current lags the voltage by 60 degrees. Now tell me what is this value? 415 divided with 20 divided with root 3. So we get 11.98 at an angle what? Minus 60 degrees what? Ampere. Okay, so we got VL, IL. So what is IL by the way? Since it is a star connected load, clearly again IL equal to what? I phase. IL equal to I phase. 11.98 at an angle what? Minus 60 degrees amperes. Okay, now you can apply the complex power formula. I'm going to write the complex power here. Let me write here only, no problem. We have a space. 3 into V phase, I phase conjugate. Okay, V phase, I phase conjugate. What is that? 3 into, what is V phase? 415 by root 3 at an angle 0 degrees. I phase. Uh, 415 by 20 root 3. 20 root 3 at an angle minus 60 degrees. Conjugate now, which will get what? Plus. Minus become plus. So you just multiply the magnitude root 3, 3 get cancelled. 415 square by 20 only we got. Yes. 415 square by 20. 86 11.25 at an angle 60 degrees. Oh, yeah, and there. Okay. What is the units? Volt ampere. This is in what? Polar form? Yes or not? Clear? Now you can convert that into what? Rectangular form now. Okay. So if you want to convert that into rectangular form, what I get? Again, four three zero five exactly plus 7457.56. Again, VA. Now I'm going to write the result here. So what is apparent power? Tell me. Apparent power, magnitude of the complex power. 8.611. This is a VA. So, but I will write what? KVA. What is the power factor angle? Positive means what? I said lagging 60 degrees. Lagging power factor. Okay, now. Then what is power factor? In short, I am going to write cos 60 lag. Cos 60 means what? 0.5? Yes, 0.5 lag. What is the active power? Real part of the complex power is called active power. What is the real part of the complex power? Active power is what? 4305, approximately 4.3 kilowatts. 4.3 kilowatts. Now tell me, reactive power. 7.457 kVR. So we got everything now. We got a complex power, we got active power, we got reactive power. But I already told you, instead of going for generally in the gate exam, I'm not going to solve using all these things. Maybe in the gate exam, you'll ask you that what is the active power drawn? What is the reactive power drawn? In that case, I will directly use one formula. What is that? I'm going to use this formula. S equal to what? VL square. Since it is a star connected load, VL square by Z conjugate. What is VL square? 415 square. What is Z conjugate? Z is what? 20 at an angle 60. Conjugate means what? 20 at an angle minus 60 degrees. Now you try using this. Same answer we are going to get. 415 square by 20. Angle when you go to the numerator, it will become what? Plus 60. I hope this is clear. In that way also you are going to get what? Same answer. Okay. Clear, sir? Right, sir. So this is what on basics. Okay. Clear? So I'll give an example for delta. You have to solve. Okay. So I'll write an example here quickly. A delta connected load has an impedance of Now you need to calculate everything here. How to calculate this? Again, I'm going to write quickly. For delta connected load, line voltage, phase voltage, both are same. Line voltage magnitude equal to what? Phase voltage magnitude. Yes or not? Which is what? 11 kV. So I'm going to take the phase voltage reference. What about the phase voltage? Tell me what is the phase voltage? Phase voltage means what? 11 at an angle what? 0 degrees kV. Line voltage also same. 11 at an angle 0 degrees kV. Quickly I'm going to write the solution. You have to watch this. Okay? Clear? I'm not going to explain much here. Right. Again I'm saying I can calculate only phase current first. V phase by Z. Okay? But what is Z? 200 plus J? 400 na? You can write this in the magnitude form. Magnitude under root of 200 square plus 400 square. $447, I'm just approximating 447.213 at an angle tan inverse 2, right? 63.435 degrees. Okay, clear? Now, what is the V phase? 11,000, 11 kV, no? 11,000, angle 0 degrees. Divide with, what is Z? 447.213 at an angle 63.435 degrees. So 11,000 divided with 447.213. So we get 24.596. 596 at an angle. This will become minus now. 63.435 degrees ampere. This is what phase current. Tell me what is the line current immediately. Line current equal to what? Root 3 times the phase current at an angle minus 30. Line current lags the phase current by 30 degrees. Now tell me, root 3 times, what is the phase current? As it is, I am going to write 24.596 at an angle minus 63.435. Okay. At an angle what now? Minus 30 as it is. So what I can write now? Line current equal to magnitude is what? Into 1.732 now. So this is 42.6 magnitude. Phase angle minus 63 minus 30. So minus 93.435 degrees. Don't think that why the phase angle is more than 90. It should not be like that. Don't come to that conclusion. It's not at all good. Please be careful. Okay. Clear? Yeah. So yeah, that is a line current. Then after that, complex power. Don't use root 3 VLIL conjugate. Either you can use what? This formula also valid. 3 into V line square magnitude of V line square by what? Z conjugate. This is also valid. Okay. Otherwise, 3 into V phase, I phase conjugate. It is up to you. Because we are already having this. But without calculating the phase current and line current, I can directly go for this formula. I can write what? See this complex power. Okay. Now let's substitute here. So I'm going to use this formula now. Okay, both formulas will give the same answer. This formula 3 into VL square. VL square is what? 11,000 square by Z conjugate. Z is what? 447.213 at an angle 63.435. But now I will get minus 63.435 because Z conjugate. Careful with the conjugate. If you are not careful, it will kill you. Okay. So now tell me 11,000 square divided with 447.213 into 3. So we get 811,693.7. So 0.811 mega volt amperes. 0.811 at an angle minus 63 point, sorry, plus 63.435 mega volt ampere. Otherwise, I can also write like this 811.693 at an angle 63.435. If your interest is in kVA, both I am writing. Okay, we'll do it in kVA only. We'll get a nice number. And if you convert this into polar form, no, 63.435. So 363 real part approximately, and imaginary part 726 kVA. Okay, so that means, so let me write the complex power, apparent power, okay. So what is apparent power here? All right, the apparent power is 811.693 kVA. The power factor angle is 63.435. But it's lagging power. Then what is active power? 363 kilowatts. What is reactive power? 726 kVA. What else? Power factor. Cos phi lag. Cos of 63.435. 0.447 lag. Right, sir. So this is how we can solve for star connection and what delta connection. There are so many gate questions on this. You can see. Okay. So, any doubts here? If you want, you can note down quickly. There is no shortcut to convert polar to rectangular, my dear. Okay, just go with the fundamental. No quick shortcut. You have to apply the same formulas. Polar to rectangular means in gate calculator, you have to do like this only. There is no direct, equation to solve complex numbers. Everywhere you have to convert polar to rectangular, rectangular to polar. Then only you can able to solve. Otherwise, no. Yes. We'll move on to the next one. So that's about one thing we need to learn about the basics, and other things what we learn in the basics part is, okay. Yeah. Now, when it comes to the transmission lines, we have 11 kV, 132 kV, 220 kV, 400 kV, like that. I want to write a clarity here and how they are what designed. Okay. So generally, okay, insulation and what conductor size or size of the conductor, how they are going to select it. Okay. So selection of insulation I'm going to write first, and then what selection of what size of the conductor. Okay. So these are the points which should be very, very careful. Selection of insulation. So on what factors, on what basis we select the insulation? For all electrical machines, believe me, for all electrical machines. When I say electrical machines, three things: generators, transformers, motors. It might be generator, it might be transformer, it might be motor. All this comes under what? Electrical machine family. So for all electrical machines, for all electrical machine, Insulation is selected based on what? Based on normal operating voltage. Normal operating voltage. You may also say normal operating voltage means what? Normal operating voltage, it's also called what? The insulation is selected based on. In other words, also we can write normal operating voltage. Let me write here voltage also. So, okay. Otherwise, one more thing also I will write. For all electrical machines, insulation is designed to withstand better. Insulation is designed. Insulation is designed to withstand a minimum of stand peak value of system phase voltage. Okay, system phase voltage. Truly speaking, peak value of system phase voltage. But if the question is given, the insulation is designed for phase voltage or line voltage. Insulation is designed for phase voltage or line voltage. Always phase voltage, because insulation is always connected between what? Conductor and ground. Conductor to ground potential is always phase voltage, no matter whether you are dealing with star connection or delta connection. 11 kV delta connected machine, 11 kV star connected machine, insulation is designed for same operating voltage 11 kV by root 3, because that insulation is always connected in the slot. That insulation is avoiding electrical isolation or providing an electrical isolation between conductor and slot area. Slot area is touching the ground. Slot area is connected to frame. Frame is connected to what? Ground. That's why the voltage across the insulation means what? Phase voltage. But why you written peak voltage means what? Worst case, the insulation can experience the peak voltage. That's why always designed for what? Peak voltage. Standard is that, but sometimes a simple question is given. Insulation is designed for phase voltage or line voltage. Answer is what? Phase voltage. Okay, no matter star or delta. Clear? Next, this is for what? Electrical machines. Okay, now for transmission lines, if you see, okay, for transmission lines, okay, for continuous operation, insulation is designed for withstand. Insulation is designed to withstand normal operation. Continuous operation means what? Peak value of system phase voltage. But there is a transient operation for transmission line. For transmission line, for transient operation, the insulation is designed to withstand. Okay, let me write here. Insulation is designed to withstand both lightning over voltage and switching over voltage. Both lightning over voltage and what? Switching over voltage. Okay, clear? Both lightning over voltage and switching over voltage. Okay, here greater than 300 kV, greater than 300 kV. So switching over voltage, SOV, switching over voltage is the criteria, because greater than 300 kV means what? Switching over voltage greater than what? Lightning over voltage. So insulation based on SOV means switching over voltage. Less than 300 kV, na, for example. Lightning over voltage is greater than what? Switching over voltage. So that's why insulation is based on what? Careful, I'm directly writing. Insulation is based on lightning over voltage. Okay. So this is also basic. Based on this also we have some gate questions. 2 gate questions are given based on this insulation selection. Okay. Clear? Any doubts here? I hope this is clear for you. Just make a note of this. All these things, I'm not going to share any PDF with you. So you better to take a screenshot and maybe you can take it for your future reference. Okay, clear? Yeah. So that's it. The next one. So yeah. Now this is what selection of insulation and selection of conductor size. Again, for all electrical machines, let me write. For all electrical machines, size of conductor is selected based on current carrying capacity. Oh. Based on current carrying capacity. For all electrical machines, quickly. Yeah, size of the conductor is always selected based on current carrying capacity. Okay. But what current? Phase current only always. Suppose it might be delta connector machine. Sometimes he will ask you that the size of the conductor is selected based on what? Sorry. Just hold on. अरे कम चल रहा अच्छा Okay. So for all electrical machines, yeah, I think it's my voice is audible now. Okay. For all electrical machines, size of the conductor is selected based on current carrying capacity. Again, I'm saying current means what? Always phase current. No matter whether it is delta connection or what, star connection, we always what? Take the phase current only, because that is the current which is flowing through the winding. That is the current which is flowing through the conductor of an electrical machine. The phase current only. The line current is a manipulated current because of star or delta. Okay. Clear? Always phase current when it comes to the design. Chalo. So now when it comes to the generators, transformer, transmission line, this is true. Sorry, transformers, generators, motors, this is true. But when it comes to transmission lines, second one, for transmission lines, yes, there is a story here. So transmission line means it might be distribution lines or transmission lines, correct or not? So let me write here distribution system first. Distribution system, I will start with what? Single phase, two wire. As per our Indian power system, single phase two wire is what? 230 volts. Okay, right. Three phase, four wire. Four wire. We have a 450 volts. There are line, this is a line voltage, but single phase two wire means what? Phase and neutral is a phase voltage. But these two are called distributors. Okay, this is called secondary distribution system. Secondary distribution system. In distribution system language, these two are called what? Distributors. Okay. Now remember, size of conductor is selected. Is selected based on based on what? Voltage drop. For a distributor, size of the conductor is selected based on what? Voltage drop. I hope this is clear for you. You might have studied all these things, but I want to give a clarity. The next one is what? Okay, 11 kV and what? 33 kV. They are also part of distribution system, which is what basically three phase, three wire. You may also say they are called what? Feeders. Feeders. And size of conductor is selected based on current carrying capacity. Okay, clear? So this is also called LV. Now this is called what? HV. Low voltage system, high voltage system. Then transmission onwards will come what? EHV system. Transmission is a part of EHV system. Low voltage and high voltage is part of what? So HV system. Okay, sorry, distribution system. And this is what secondary distribution system. But what about this? Three phase, three wire, 11 kV and 33 kV. This is called what? Primary distribution system. Okay, careful. Take a screenshot of this. It will be helpful. It will be helpful to you. Okay, clear? Understand? It will be helpful for your quick revision. Definitely. Chalo. Yes, I hope it is done. Okay, now tell me. So when it comes to this is about what? Distribution system completely. Now I'm going to write transmission system quickly. Size of conductor for transmission system, how it is selected. Now tell me. For transmission system, size of conductor is selected based on what? Okay, I already mentioned that. EHV, extra high voltage line. Transmission system will start with what? EHV line. What about EHV? 66 kV comes under EHV. 110 kV, especially in Kerala and Tamil Nadu, we have 110 kV system and 132 kV. Yes, even what? 220 kV also. Okay, 220 kV also. It comes under what? EHV. But complete transmission system is what? I'm going to write here. Three phase what? Three wire only. 66 kV, 110 kV, 132 kV. But here size of conductor is selected. Conductor based on current carrying capacity. But when it comes to the 220 kV onwards, size of conductor is selected based on size of conductor. Sometimes the question will be given like line design is based on. Line design means conductor design is based on corona, because 220 kV onwards corona will come. So our main focus is to reduce the corona. Okay. So if you want to reduce the corona, you have to go for what? Higher size of the conductors. So that means let's calculate the size of the conductor as per what? Current carrying capacity. But you calculate the size of the conductor as per corona, that will be slightly higher size. So that's why. So size of the conductor is selected based on corona. Now, MEHV, modern extra high voltage, that is what? 400 kV. Again, size of the conductor is selected based on corona. Next, ultra high voltage, UHV, 765 kV and above. In future, again, size of the conductor is selected based on what? Corona. Okay, clear? So that means for 220 kV and above, for complete transmission network, the size of the conductor is selected based on what? Corona only. So I hope this is clear for you. Any doubts here? Any doubts here? Now, I'll just take 10 more minutes to complete the basics. I want to quickly explain what the conductors also. Okay, so maybe in the gate point of view, there may not be a question from conductors, but better to have some idea about what conductors. Okay, quickly. So generally solid conductors we have. Okay, let me write quickly. Solid conductors. Solid conductors only preferred for what? Not preferred for transmission system and distribution system, but where we prefer? Only for earthing and grounding. Why solid conductors are not preferred for transmission and distribution system? It's just simple reason, Rabai. It's because of what? It's rigid nature, because of high skin effect. You know what is skin effect now? The current will be concentrated through the skin region of the conductor. Center portion of the conductor, very less current is flowing. That is what? Skin effect. To reduce the skin effect, to increase the flexibility, to reduce the rigid nature, conductor should be easily bent. Then only what? Transportation becomes simple. Then only you can make the conductor in the form of foil. We use what? Standard conductors. Okay. So it is standard conductors we use. But standard conductors means what? We have different types of conductors. So all aluminum conductors, AAC conductors, all aluminum conductors, which all the strands made up of aluminum. I'm not going to write directly, I'm saying here, all the strands are made up of aluminum, AAC conductors, ACSR conductors, and AAC conductors. AAC for special application, AAC for what? Distribution system, ACSR for what? Transmission system. Okay, clear, sir? Because of standard, standard conductors having what? Less tensile strength. So that's why what? So there is a sag is more. To increase this, to reduce the sag, we are going for what? Steel as a reinforced material. So ACSR conductors are used for what? Transmission system. AAC conductors for special applications. Special applications generally for what? So for longer spans in distribution system. Longer spans in distribution system, we go for what? AAC conductor. AAC conductors having tensile strength equal to ACSR but lighter weight. Okay, clear, sir? So I want to give an application part only. I'm not going in details of this. It's not important for gate exam point of view. But AAC conductors, remember, it is used for what? Both transmission and distribution, only for special application. In distribution system, where longer spans are used. Longer spans are generally at road crossings, river crossings, railway crossings, where we need longer spans in distribution system, then go for what? AAC. And shorter spans anyway, we go with what? AAC conductors in distribution system. But in transmission system, where we use these AAC conductors. Okay, so in transmission system, these AAC conductors are used where we use lightweight tower construction. Lightweight tower construction means in forest areas. and what mud areas, swamp areas, where the soil is what very loose, okay, loosey nature of soil. If you put a strong foundation or heavy tower, it will be shrinking into the ground. So that's why, okay, we need a lightweight tower. If you are using lightweight tower, means lightweight conductor. AAAC conductors are lighter in weight compared to ACSR. So ACSR is not suitable for lightweight towers. So in that case, what we use, what AAAC conductors. So that's about the conductors. Okay, clear, sir? So I'm not going much details of this. This is enough. And at the end, what is skin effect and proximity effect? You just have a look up that. Okay, so that's about the basics of power system. The first chapter we finished. Now we'll move on to the second chapter. Okay, just 2 minutes break I will take. So then we'll go to what? Second chapter. Only 2 minutes, not more than that. Okay. So let me write the second chapter here. The basics is done. Yeah, no power cut, don't worry. So we'll start now quickly. All right. Okay, chalo. So, yeah, line parameter calculations we'll see quickly. So, we are going to calculate the transmission line parameters here, the resistance, inductance, capacitance, and conductance. Yes or not? Okay. So, a transmission line is simply represented with what? These four parameters, right? So, there is a line connected between what? The sending end and receiving end. We have a resistance and inductance as series elements, and capacitance and conductance are what? Shunt elements. So our focus is mainly to calculate the resistance, inductance, and what? Capacitance and conductance. But one more thing, all these line parameters are what? Distributed in nature. They are not concentrated. Already discussed this. All line parameters are distributed in nature. Okay. So what is the meaning of distributed parameter? Every small section of the line you see, in that there exists a resistance, inductance, capacitance, and conductance. So that's why the line parameters are always what? Distributed in nature. So one should notice this. Okay. Clear. So the point is, how to calculate the resistance of the line? It's very simple. The resistance of the line, the conductor is having certain length. The resistance of the line is what now? Rho L by A. But remember, this is what? DC resistance. But to calculate the AC resistance, we are going to use what? 1.6 factor. Why we are using this 1.6 factor? To account for what? Skin effect. Due to the skin effect, the resistance will increase. Even though you are using stranded conductor, definitely there is a skin effect in transmission system, because every strand itself is a solid conductor. Whenever the conductor is carrying an AC current, definitely there is a skin effect. For DC, no skin effect. That's what I'm trying to say. AC resistance is always greater than DC resistance, approximately 1.6 times. This is a commonly asking question in our the competitive exams. Okay, chalo. So that's about the resistance calculation. There is nothing great about resistance calculation, but the resistance calculation influenced by four major parameters. Number one, spiraling. We use what? Spiraled conductor. It's not a straight conductor. The conductor is what now? Spiraled. Something like this. It is spiraled. Okay. All the strands are what? Spiraled. So successive layers of stranded conductors are always spiraled in opposite direction. Then only there is a good mechanical holding between the conductors. That's why, since it is a spiral conductor, you take one strand, you straight it, don't stretch it, right? Don't stretch it, you straight it. Then the length of each strand is 1 to 2 percentage higher than 1 to 2 percentage higher than the length of original stranded conductor. Here the length means what? Stranded conductor length you consider, but strand length is what? 1 to 2 percentage more. That's why if you consider the spiraling effect, the overall resistance will increase it by 1 to 2 percentage, both DC and AC. Yes, that is the first factor. Spiraling will affect the what? Resistance calculation. Number two, what is going to affect the resistance calculation is, that is temperature. So because all our conductors are positive temperature coefficients, you might have studied conductors, positive temperature coefficients, semiconductors, insulators, negative temperature coefficients. That's why, because of increase in temperature, atmospheric temperature or conductor temperature, whatever you say, so better to say conductor temperature got increased. Then definitely what happens? Definitely what happens? Resistance will increase. Okay, so you know this formula, well-known formula. The resistance at one temperature RT2 equal to what? RT1 into 1 plus alpha times delta T. But delta T is the T2 minus T1 temperature difference. RT2 is the resistance at what temperature at T2. RT1 is the resistance at what temperature at T1. 1 plus. Why? Because it is a positive temperature coefficient. Alpha is the temperature coefficient of the material. It is in per degree centigrade. It's a well-known formula. You are studying this formula from intermediate onwards. Okay. So the point is that alpha is high for what? Copper than aluminum. Copper conductor having what? Higher, the temperature coefficient than what? Aluminum. So just remember that. Yes, whenever the temperature increases, DC resistance will increase, AC resistance will increase, both. Whenever spiraling effect is considered, resistance will increase by approximately 1 to 2%. Okay, spiraling effect is considered, resistance is increased by 1 to 2%. Remember that. Okay, simple question can be asked from that. So then the next factor is what? Frequency. Yes, third factor which affects the resistance calculation is the frequency. Yes, frequency increases, skin effect will increase. Then DC resistance will not change, AC resistance will increase. But we don't need to worry about because Indian power system always what? Frequency is 50 Hz. So there is no question of what increasing of frequency. But remember this, if frequency increases, resistance calculation will increase. But AC only, but not DC, because DC, no skin effect. And mu R value of the conductor. Yes, we are using ACSR conductors for transmission system since the steel having some mu R value. Steel having very good magnetic properties. Every magnetic material is characterized by its mu R value. So you know that. So if mu R value increasing, mu R value also called what? Magnetic property of the conductor. That also affects the resistance calculation. That is a fourth factor. Magnetic property of the conductor. Mu R value increases. RDC will remain same, but RAC will increase, because if mu R value increases, skin effect will increase. Yes, skin effect increasing means what? Definitely AC resistance will increase, but DC resistance will remain same. I hope this is clear for you. So that's about the resistance calculation. There's nothing great. Now directly we'll jump onto the inductance calculation for what? Single phase transmission line. That's it. I'm not going for what method of calculation of inductance. I'm just write the formulas. We'll see that. That's enough. And at the end, I'm going to explain the concept of GMD and GMR, because there is a chance of getting a question from what? Even GMR also. Okay? Clear? Understand, sir? Okay? So now directly inductance and capacitance for single phase transmission line. Okay? Yeah. We'll go to the next slide. Oh. Now here onwards, analog started, I think. Okay. So, all right. Now, the point is, yes, the inductance calculation. Directly, I'm writing single phase transmission line. Single phase transmission line, what is the inductance? See, for single phase transmission line, there are two things we should be very, very careful while even the gate exam also, both the way question is given. He will ask you, calculate the inductance of single phase line, calculate the inductance of single phase circuit, both are not same. Circuit means what? Both, two conductors, LA and LB. For example, there are two conductors, single phase transmission line, conductor A, conductor B, okay? They are separated by a distance called what? Let's say D. D is the spacing between the conductors. Remember always, the inductance means self-inductance and mutual inductance. Self-inductance has two parts. Inductance due to internal flux linkage, inductance due to external flux linkage. Mutual inductance means only one thing. Self-inductance depends on what? Radius of the conductor. Mutual inductance depends on what? Spacing between the conductors. Okay? Self-inductance always depends on what? Radius of the conductors. Mutual inductance depends on what? Spacing between the conductors. There's a proof for all these things, but I'm not going into the proofing of all these things. Okay, this is not the time to learn about that, but just remember these things. Okay, so Tell me, the conductor A and conductor B. Okay, let's say conductor 1 and conductor 2 also, not a problem. Okay, radius of conductor 1 is what, R1 here, radius of conductor 2 is what, R2 here. Yes, the spacing between the conductors is D. Now let me write the expression for LA. LA is what now? 2 into 10 power minus 7 ln D by what? R1 dash. Yes, this dash will come. Dash. The dash, why we are taken? That is just to account for what? Internal flux linkage inductance. There is an inductance due to internal flux linkage, inductance due to external flux linkages. There's a big story behind that, big derivation behind that, but believe me, it's all thing not required, just R1 dash. Okay, so just if we consider R1 means what? You are indirectly neglecting the inductance due to external flux, sorry, internal flux linkage. You have to take what? R1 dash. Again, while solving the problems, remember this, mark my words, while solving the problem, same question is given, people will forget to take R1 dash. People will just substitute R1, that's it, end up with wrong answer. It should be R1 dash. R1 dash is 0.7788 times R1. Okay, so let me write here R1 dash, and moreover, the formula is what? Always Henry per meter. R1 dash is 0.7788 times what? R1. Now similarly, what about LB? 2 into 10 power minus 7 ln what? D by what? R2 dash. Okay, again this is what? Henry per meter. Okay, clear? Again R2 dash also same, 0.7788 times R2. Okay, this is LA separately, LB separately. Okay, one more thing, always remember, if you want to replace, suppose if mu r is 1, sometimes mu r is given in the problem. Till now there is no gate question with mu r value. Believe me, till now there is no gate question with mu r value. If mu r value not given in the problem, take it 1. Okay, if mu r equal to 1 also given, fine. If mu r equal to 1 means you don't need to worry, you can use this formula as it is. But if at all mu r value is given, you should be always careful. What? Mu r is going to affect what? Inductance due to internal flux linkage. I said clearly there is a self inductance and mutual inductance. Later I am going to write that. You don't need to worry. So, but the point is, the self inductance has two parts: inductance due to internal flux linkage, inductance due to external flux linkage. This inductance due to internal flux linkage is definitely affected by mu r value. Okay, so to consider all these things without avoiding the confusion, Rabbi, you don't need to worry about what is internal, what is external, what is self, and what is mutual. Believe me, the formulas. These formulas, but mu r is 1 means, okay, fine. Mu r 1 means what? If you want, you can replace like this. If you want, you can replace. Mu r equal to 1 means there is no need to replace, directly you calculate. But if you want, I can replace ln d by r dash like this. Ln d by r dash, remember always 1 by 4 plus what? Ln d by r. Remember always, this is always valid. Okay, clear? Ln d by r dash can be replaced with what? 1 by 4 plus ln d by r. And mu r not equal to 1. If that is the case, same ln d by r dash, you can replace like this. Mu r by 4 plus ln d by r. I hope you noticed this. In the second part, r dash is not came. The dash is what taken care by what? This 1 by 4. Okay, clear? Understand? So that's it. Simple mathematics behind this. I don't want to go into that stuff. It's not important. Just remember. Okay. I hope this is clear, sir. Okay, so this much is okay. Now, so indirectly, yeah, I will go for what? Single phase transmission line. See, truly speaking, single phase transmission line, practically you ask me, R1 equal to R2. R1 equal to R2, that's it. Why R1 equal to R2 means? Simple reason, both the conductors will carry same current. Phase conductor, the conductor which come to your house, the conductor which is going from your house, two conductors will come to your house, phase and neutral. The current will take the written path through the neutral conductor till the distribution transformer. Yes or not? That's fine. No doubt, believe me, phase conductor and neutral current will carry what? Same current. Same current means what? The size is same. Okay, but maybe if the question is given like that, I can able to solve. That is the reason I given like this. Anyway, so we'll go to the next part. So for a single phase transmission line, this is LA and LB. But based on this LA and LB, I can write two things. What is the inductance of single phase line? What is the inductance of single phase circuit? Okay, these things are very important. Please take a screenshot of this. I am not going to share any PDF. because the PDF is it is not going to be saved here. Okay, so please, okay, take a screenshot wherever it is required. Chalo. Now the thing is that, okay, the question will be asked like this: inductance of single phase line is what, and inductance of single phase circuit is what? Okay, I don't think so whether this color is visible or not. Yes, is it fine? Okay, fine. Chalo. So inductance of single phase transmission line. Yes, I can use that. Yeah. L single phase. Single phase transmission line means always you go with what? Average inductance. Average inductance means what? We have a two conductors. Average inductance means what? LA plus LB by 2. Yes or not? So if you solve that, 2 into 10 power minus 7 common. So I'm directly writing ln of what? D by R1 dash into what? R2 dash. Henry per meter. So you can convert this into millihenry per kilometer also. There's nothing wrong. 0.2. 10 power minus 6. 0.2 times 10 power minus 6. Ln what? Same. Now this will be what? Millihenry per kilometer. Because generally we get a considerable number for what? Millihenry per kilometer without any multiplication factor. Okay. Clear. Now this is for inductance of single phase transmission line. Now the next one is inductance of single phase circuit. How it would be? Single phase circuit. Otherwise, total inductance of single phase transmission line or loop inductance all are same. Okay, loop inductance, total inductance, all the things are what? Same. The question is given anyway, so then the answer is what? Okay, okay, let me write here first the basic formula wise. LA plus LB. Yes or not? Total means LA plus LB. Indirectly, it is 2 times L single phase, na? Yes or not? It is 2 times L single phase. So, which is what? Henry per meter. Okay? Clear? Any doubts here? Yes. Okay. So, yeah. So, that's about so inductance of what? Single phase circuit, my dear. Okay. Clear. So careful with this. Again, if you want, you can take a screenshot of this. It will be definitely useful. It will be definitely useful. The gate questions are very simple and straightforward from this topic. Only from the formulas only. Okay. Believe these formulas, definitely you can answer. That's it. Don't think about much about how you got these formulas. What are the basics behind this? Nothing is required. Just with clear mindset, take these formulas and see the problem, what is mentioned in the problem, and you can answer. Okay. Chalo. Clear. I hope this is clear for you. Chalo, we'll move on to the next one. So here, but basically R1 equal to R2 equal to R. That's why in practice R1 equal to R2 equal to R. That's why L single phase means what? Okay. Sometimes he will ask you self-inductance. I can split this into two parts. I can write like this if you want. Ln 1 by R dash. Yes. So this is what self-inductance part. That depends on radius of the conductor. This is what mutual inductance part. That depends on what spacing between the conductor. That's what I'm trying to say always. And again, I said one thing. Self-inductance has what? Two parts. Inductance due to internal flux linkage, inductance due to external flux linkage. If you want that, I'm going to write here 2 into 10 power minus 7 what? Ln 1 by R dash na. Again, I can split this into two parts. What? 2 into 10 power minus 7. Okay. 1 by 4 plus 2 into 10 power minus 7. Yes. Ln 1 by R. Henry per meter, right? Now, indirectly, this is what? Inductance due to internal flux linkage. What about this? Inductance due to external flux linkage. Okay. It is very wrong to call. It is not correct to call L internal, L external. That means internal inductance, external inductance. No. The meaning of L internal means it is the inductance due to internal flux linkage. That is the correct way to call. It is the inductance due to external flux linkage. You notice inductance due to internal flux linkage is always constant. It is not depends on size of the conductor, spacing between the conductors. But inductance due to external flux linkage, that depends on what? Yes, size of the spacing size of the conductor. I'm sorry. And again, mutual inductance depends on what? Spacing between the conductors. Okay. I hope this is clear for you. So if mu r is given, what? Here mu r will come. Mu r by 4. Yes or not? You understand this now? Ln 1 by R dash I am replacing like this. So I have freedom to write like this. Ln 1 by R dash. I can replace with what? Okay, this is mu r equal to what? 1. D equal to 1 here I am taken. Okay, earlier I explained this formula with D. Okay, that's it. Oh shit. Okay, again, ln 1 by R dash. I can replace with what? Mu r by 4 plus what? Ln 1 by R. Okay, clear? Careful. So that's why the internal inductance due to internal flux linkage, here mu r will come. So if mu r is there, then L internal will increase. Otherwise, self inductance will increase. There's nothing wrong to say that. And mutual inductance formula is what? But remember always, this dr must be in what? Meter. Always remember, it's not in centimeters, it's not in kilometers, it's always in meters. Take a screenshot of this if you want. Okay, this is again very, very important. Okay, clear? Clear? Chalo. Right. Now we'll solve a question on single phase transmission line. With that we'll proceed. Try this question, this will cover everything. mu r equal to 5, then now you try this. What is L circuit? What is L single phase? With mu r value. Do it fast. Do it fast. Try it. Try it. Yeah, do it now.
మళ్ళీ అడుగుతారు కానీ మళ్ళీ 1% కలిసి తెచ్చినట్టు.
Okay. You అందులో ఓకే చెప్తా. Okay, done now? Anyway, I'm going to solve quickly since we have very less time. Yeah. So how to calculate this? Very simple. Okay. Yeah. Try to use LA and LB separate formulas. LA you have to calculate separately. So I'm writing here 0.2. Ln d by r. Okay, if you want, I will write in millihenry per kilometers. Everything. Okay. Quickly. 2 into 10 power minus 7. Yes. Ln d by r1 dash. Okay. But r1 is what here? 0.02 meters. It is in okay, r1 is what? 0.01 centimeter. No? 1 centimeter, 0.01 meters. R2 0.02 meters. Anyway, distance between the spacing is what? D. That is what 2 meters given, and mu r value also given. Okay, ln d by r1 dash. Quickly I am writing 0.2 ln what? D by r1 dash. What is this? Millihenry per what? Kilometers. And if that is the case, 0.2 ln. Okay, okay. There is a 0.2 ln. Okay. So mu r by 4 plus mu r by 4 plus ln d by r1. Let's substitute and tell me, but this is in what? Millihenry per kilometer. Quickly, what is this value? What is this value? Yeah, 0.2. Let's substitute one more step. Mu r 5 by 4 plus ln. What is the spacing between the conductors? D, that is what? 2 meters. And r1, yes, r1 is given 0.01. So ln 200 first plus 5 by 4, which is 1.25 into 0.2. So 1.3096 millihenry per kilometers. What about LB? Okay, again, I'm directly writing now. Please don't confuse. 0.2, this formula I'm writing. Mu r by 4 plus ln d by r2. Again, millihenry per kilometers. By default, this is in millihenry per kilometers. Is that okay, right? Yes. 0.2 into 5 by 4 plus ln d 2 by 0.02 ln 100, right? Ln 100 plus 1.25 into 0.2, which is approximately 1.171. That's it, L circuit. .48. L single phase. Divide with 2. 1.24. There's nothing great here. Okay, just have a look. This is how we need to solve. If R1, R2 given separately and mu r also given, then this is the only approach to solve. Don't use any other methods. We'll solve a simple question, general questions which is asked in GATE exam. Okay. Okay, we move on to the next question. So commonly asking question is like this in GATE exam. Single phase transmission line has two conductors of radius. So 2 centimeters and spacing between them 2 meters. If this is the case, now directly we go for what? Simple formula. What is the formula? So L single phase means what? 2 into 10 power minus 7 ln what? D by R dash. Because L1 R1 equal to what? R2. Yes. If that is the case, I can also write 0.2 ln what? D by R dash. R dash. Careful. Here many people will mistake. They will directly substitute what? 0.2 ln D. D is what? Point to ln D. D is what now? 2 meters. They substitute what? R dash is what now? R is what? 2 centimeters means 0.02 what meters. So they will substitute 0.02. That's it. End up with wrong answer. This is the common mistake. If same question is given, believe me, 30 to 40% of the people will write like this. End up with wrong answers. So now, what is correct? What is correct? In the denominator, it should be what? R dash means what? Let's try this. Point 971. What about L circuit? 2 times L single phase, na? Or L average, na? What is this? We get 1.942 millihenry per kilometers. That's it. Nothing great about it. Only single phase system you have to treat what? Carefully. Where there is a chance of asking a question. L single phase and what? L circuit. So if you want, you can take a screenshot of this. Okay. Okay. Next. We'll move on to the capacitance of single phase line. The only thing is what, believe me, there is a two things again when it comes to the capacitance to neutral, capacitance of single phase line. Okay, so I'm going to write the formulas directly, please. Okay, so write the next. That's about the inductance. Now, again, capacitance to neutral of a single phase transmission line. So that is what we call CAN. We get 2 pi epsilon naught ln d by r. There is no r dash here. The reason is very simple. While calculating the capacitance, what is the formula? Maybe charge of the capacitance is C, voltage of the capacitance is C equal to what? Q by V. But there is no internal charge. Charge inside the conductor is 0. But while calculating the inductance, what is the formula? Current through the inductor is I, flux linkage is lambda, L equal to what? Lambda by I. There is an internal flux. The flux linking the conductor inside is what? Not equal to 0. To account for this, what? We define what? R dash. Since there is no internal charge, there is no concept of what? R dash here. It is what now? R only. So that is what you need to see. It's not what? R dash, it is what? R. So capacitance calculation, we always take R. There is no concept of R dash. Please be careful this. Again, the people will mix up both. End up with wrong answer. Capacitance R dash will not come. Okay. So ln d by R, but this is what? Farad per meter. Now, next one is capacitance of a single phase transmission line. Capacitance of a single phase transmission line. What is the formula for that? CAB we say. That means capacitance between two conductors. CAB equal to what? CAN by 2. Believe me, I'm not going in details of how it came. Okay. So what I get? Farad per meter. That's what CAB. Okay. And CAN. Is it clear? Now, there's one more thing also very important for what? Capacitance. That is what? Charging current. What about charging current of single phase transmission line? Charging current of single phase transmission line means what? Always remember, we need to use what? Phase voltage only. But single phase means what? By default, voltage given is the phase voltage. So charging current equal to what? V into omega into, it's not CAN, it is always what? CAB. Okay, clear? So if this is in what? Farad per meter, the answer is in what? Ampere per meter. Okay. So these are the three things you should be very careful. Again, we are going to solve a problem here. Okay, quickly. So if you want, you can take a screenshot of this. So this much is enough for what? Capacitance of single phase. With this, we can finish what? Single phase system very quickly. Chalo. We'll take one problem so that you can get a clarity on this. Okay, quickly. So again, single phase transmission line. 11 kV, 50 Hz single phase transmission line has two conductors of equal radius of, let's see how the people will confuse by reading the question. Equal radius of 1 centimeter and spacing between them remains 2 meters. Now CAN watt, CAB watt, charging current watt. Now the first confusion is 11 kV means what? What is this? Line voltage or phase voltage? People will write what? Line voltage. 11 by root 3 is the phase voltage. They will use what? Charging current 11 by root 3. That is blunder, because single phase 11 kV by default voltage is 11 kV. But why this confusion came? Because we studied now 11 kV line we have. That is a 3-phase line. 11 kV by root 3 is the phase voltage. This is what will be there in our mind. There we end up with wrong answer. 11 kV line is there in outside. That is what? 3-phase, 3-wire line. That is a part of what? Distribution system, primary distribution system. Okay, fine. But question is not like that, na? It is a single phase 11 kV line. He is only saying 11 kV single phase voltage. Phase voltage 11 kV. Yes or not? Clear? So that's why you should be very careful. Okay, chalo. So what is the voltage now? Phase voltage only 11 kV. That's it. Because it is a single phase. Chalo. So V is what now? 11 kV for us. Now I'm going to write first CAN formula. 2 pi epsilon naught ln d by r. Let's substitute. 2 pi epsilon naught means what? 8.854 into 10 power minus 12 ln d. D is what? 2. Radius is what? 2 conductors equal radius 0.01. The units are farad per meter. If I solve this, what I get? Make it fast. Ln 200 no in the denominator. Approximately 10.5. I can also write this is what? 10.5. This 10 power minus 12 I can write nanofarad. Nano means 10 power minus 9 gone, but one more 10 power minus 3 coming into the denominator. Nanofarad per kilometer. There is nothing wrong to write like this. Okay. Any doubts here? That's what CAM. CAB is off of this. What is the charging current? Again, while calculating charging current, use what? Farad per meter. Careful. Use this for charging current. Because we want ampere per meter. So V 11 kV. Omega. Capacitance. This much ampere per meter. Let's substitute now. I'm sorry, this is CAB, na? This is wrong. Here what? Not CAN. 5.25 into 10 power minus 12. So we got 1.8142 ampere per meter. Otherwise, 18.142 into 10 power minus 6. So milliampere in the numerator. We can manipulate depending on what requirement. Okay. So that's about what the capacitance of the single phase transmission line and the calculations regarding that. Okay. All right. Now we'll see concept of GMD and GMR quickly. Right. So next 30 minutes we are going to close this. Okay. That is the line parameter calculations. Okay. Chalo. What is the concept of GMD and GMR? All right. When we use GMD, concept of GMD. Okay. Again, GMD means what? Geometric mean distance. GMR means what? Geometric mean radius. Okay. GMD going to affect what? Mutual inductance. That's why it is also called mutual GMD. GMR is mainly affect what? Self inductance of the line. It is also called what? Self GMD. There is nothing wrong. Okay. But when we use this, if system has more than one conductor per phase, more than one conductor per phase, suppose single phase only you take it. This is what? Three conductors A forming A. There are two conductors forming B. 1, 2, 3. Let's say 4, 5. You may also say this is a phase group. This is what? Neutral group. So if you want to calculate the inductance with respect to this single phase line, phase group means this is carrying a current of I at an angle 0. What about this? Carrying a current of I at an angle 180 or minus 180. Otherwise, this is simply I. This is what? Minus I. Yes or not? But if you notice this, there are three conductors in one group, two conductors in what other group. With respect to them, more than one conductor per phase, you say. More than one conductor per phase. Yes, you have to use the concept of GMD and what? GMR to calculate the inductance and capacitance. Okay, clear? Understand? So, but how to use this concept of GMD and GMR here? But careful, when we use the GMD, while calculating the GMD, you need to careful one thing. While calculating the GMR also, you need to think about one thing. Okay, that is what? GMD means outside the group you need to apply. Outside the group, GMD. GMR, within the group. Otherwise, you may also say like this. If conductors are belong to same phase, then GMR. Within the group means, what is the meaning of group? In a group, all the conductors belong to same phase. In a group, all the conductors belong to same phase. So that's why I'm saying, within the group, you apply what? GMR. Outside the group, okay, that means what? Phase to neutral. Otherwise, A phase to B, B phase to C, you apply what? GMD. Concept of GMD is applied between the conductors or group of conductors if they are carrying what? Different current. But the concept of GMD is carrying what? GMR is applied between the conductors or group of conductors which belongs to same phase. Not belongs to same phase, GMD. Belongs to same phase, GMR. If you remember this, and the calculations become what? Very, very simple. Okay, then after that, what is inductance? 2 into 10 power minus 7 ln what? GMD equivalent by what? GMR equivalent. Henry per meter. I'll take the same example only, okay, to calculate. What about the capacitance? Okay, GMD by what? GMR. Again what? Farad per meter. But notice one thing. Please be careful here. While calculating the GMR, you replace what? R dash with what? R. R dash with what? R. Okay. So that's why if the question is given, is the concept of GMR or self GMD, both are same now, valid for inductance or capacitance? Give me the answer only inductance. Don't give me the answer capacitance. Because GMR means R dash only. GMR means with R dash. Okay. But you replace everywhere R dash with R, then we modify the definition of GMR. That's what I'm saying. Okay. So that's why if the concept of GMD is valid for inductance or capacitance or both, answer is both. GMD you don't have a problem. But concept of GMR is valid only for inductance, not valid for capacitance. But with modifications, we make it use it for what? Capacitance also. What modification? Replace R dash with R, because there is no concept of R dash for capacitance calculations. Okay, is that clear, everybody? Chalo, that's it. So now we'll move on to the next slide. Now tell me, so there is a single phase line only, 3 conductors here. Maybe 3 conductors. There is some distance here, 1, 2, 3. Don't assume 3-phase system, right? 3 conductors, that's it. Here what? Maybe 2 conductors. Single phase transmission line. These 3 conductors are forming phase group carrying a current I. These 2 conductors are forming a neutral group carrying a current minus I. Then what is GMD here? GMD means what? Outside the group. GMR means what? Within the group. Okay, now let's see. So let's say this is what? A group, this is what? B group. Now I am going to calculate GMD of group A directly. What is the meaning of GMD of group A? It is effective distance from what? A group to B group. But while applying the GMD, you have to look for what? Outside the group with respect to every conductor. Now tell me, outside the group means what? With respect to conductor 1. Let's see how many terms we get. D14. 1 to 4 distance, right? Then 1 to 5 distance. Outside the group, not within the group. Outside the group. D14, D15. Only 2 conductors, 2 terms with respect to 1. With respect to 2 also. D24, D25. That's it. Not within the group, only outside the group. If you write D21 and D23, that is wrong, because that is for GMR, not for GMD. Okay. D24, D25. Then with respect to 3, D34. Tell me how many terms you are multiplying. Simple logic. This is what? Total what? 6 terms. So that's why it is 6th root. Okay. Clear? But story is not over yet. Why? This is not correct. Completely not done. Okay. So we are written. Okay, I'm sorry. This is correct only, because with respect to conductor 1, conductor 2, conductor 3, you are written the terms. That's it. Okay, fine. Okay. 6 terms, 6th root. Nothing wrong. Now tell me GMD of group B. Now group B means what? You have to start from group B. What is the first conductor of group B? First conductor of group B, 4. D4, outside the group. D4 1, D4 2, D4 3. That is the procedure. Hold the procedure. That's it. Don't look for why I written like this. I'm not going in that details. Then with respect to 5 also, you have to write the terms. D51, D52. Outside the group only, not within the group. How many terms? 6 terms. Check here. Group GMD of group A and GMD of group B, always you get same. Valid only for single phase, not for 3 phase. It's a single phase system. Only 2 groups. Group A to group B, group B to group A, distance is same. What is the meaning of GMD of group A? Effective distance from group A to group B. What is the meaning of GMD of group B? What is the meaning? Effective distance from group B to group A. That's why what? Same. So that's why. What is GMD equivalent? Again. That's much. That much is enough. Clear? GMD equivalent. Now tell me, okay, again I am saying, if we calculate GMD of group A, that's enough. Why it is written square root? Because only I am multiplying what? 2 terms. That is the logic. If you are multiplying 2 terms in the root, square root. If you multiply 6 terms, 6th root, that's it. It is 6th root. I hope this is clear. Now tell me, what is GMR? GMR of group A. Again I am saying, within the group. Within the group means what? You start with conductor 1, D11, D12, D13 within the group, but not yet done. With respect to 2 also, D21, D22, D23, Not yet done. One more thing. D31, D32, D33. But how many terms here? Just count. Ninth root. But what is this D11? R1 dash. What is this D22? R2 dash. What is this D33? R3 dash. R1 dash means 0.7788 into R1. But inductance calculation, capacitance calculation, D11 substituted as what? R1. That is only different, nothing else. We are going to solve one question also based on this, no need to worry. Okay, quickly we are going to solve that. Chalo. So that's about GMR of group A. But don't come to a conclusion that GMD of group A, group B same. Similarly, GMR of group A and group B same. No, it's not that. Need not be same. Maybe sometimes it may be same. Okay, but generally I'm saying need not be same. But GMD of group A and group B, irrespective of number of conductors in group A, irrespective of number of conductors in group B, it is always same. Okay, but GMR of group A and group B need not be same. Careful about this. Mark this. GMR of group B. What is GMR of group B? Tell me. Again, you start with what? Second group. Within the group, not outside the group. GMR means within the group. GMD means outside the group. That is the only logic. Nothing else here. Very simple. Okay. Within the group, GMR of group B. How many conductors? Only two conductors. D44, D45. Next. D55, D54, D55. Okay. Again, D44 means what? R4 dash. D55 means what? R5 dash. That's it. This is again fourth root. How many terms? 4 terms. Fourth root. Otherwise, how many conductors here? 2 conductors. 2 square. How many conductors here? 3 conductors. 3 square. 9 terms. Okay. This is clear. That's how we can calculate what GMD and GMR. Okay. Clear, sir? So now I'm going to give one example quickly. You're going to solve that. Okay. So then calculate the inductance and what capacitance also. Okay. One example. That's it. Because if you ask me, generally the question will be from single phase line only. 3-phase line will complete what? Very quickly. Only formulas and one problem we are going to solve. Okay. There's nothing great about 3-phase line. Okay. Anyway, we have bundle conductors. I will explain quickly what is bundle conductors. That's it. Okay. Nothing great here. Right, sir. Now, let's take this problem. You have to solve this. Radius of all conductors is 1 centimeter here. Quickly you solve this. $20 centimeter means, first of all, If I want to solve now, first I will see like this. 20 centimeters means I will convert this into what? Meters. 0.2 meters. So what about this distance? And this distance same. What is that? D12. Because it forms a right angle triangle now. Because that is required actually sometimes. D12 and what? D23. Same. Again D21 and D32. All are same. What is that? Under root of what? This distance 2 and this distance 0.2. So what is that? Because this is required to proceed. So this is the first thing I need to be see. After this question, I am going to give short break. Don't need to worry. Almost 2 only, 2.01 approximately. 2.01 meters. Okay. Now think about what is the answer. Now I'm writing here GMD of group A. Group A means according to us, how many conductors? Again, this is also I will focus. Group A means what? 1, 3. Group B means what? 2, 4. That is the numbering given. We just follow. That's it. Okay. So now tell me, what about GMD of group A? I don't want to solve GMD of group B and GMD of group A separately. Both are same. Directly group A I am writing. Within the group or outside the group? Within the group means D11 I will write, but it is outside the group. GMD outside the group. Careful, careful. D12. D12. Then D14. Then D32. Then D34. Outside the group. Fourth root. 4 terms. Substitute. What is D12? 2.01. What about D14? D12. I'm sorry. D12 is what? 2. 2. Think it. Think it. Again, D32, 2.01. 3 to 2 distance. Fourth root. Which is approximately 2.005. Have you noticed one thing? Have you noticed one thing? Actually, spacing between the subconductors, because these two belongs to same phase. That's why I'm saying subconductors is very, very low compared to what? Spacing between the, different groups. Different groups. Spacing between the conductors, spacing between the subconductors, both are different. Spacing between the subconductors means what? Within the group, what is the spacing? Which is very, very less. This is what we call bundle conductors. While calculating the bundle conductors GMD, we neglect what? The effect of bundling. Yes, these two conductors belongs to same phase. That is very small when compared to what? Group A to group B distance. That's why we neglect here. But if it is 2 meters, yes, it is considerable. That's why don't neglect now. I'm saying you need to calculate based on the question. But practically, this is the situation. This is a practical situation, I'm saying. No need to consider what? No need to solve using what? Some procedure of calculating GMD of like this. Okay, practical case, I'm saying. Because GMD is approximately 2 only. 2.005 approximately 2. Anyway, so this is what GMD equivalent also. Directly I'm writing because I don't need to write what? GMD group B. You get same. You try it 2.05. And GMD equivalent also you are going to get same. 2.05 meters. Now GMR of group A. What is GMR of group A? Yes, D11, D13, D31, D33. Okay, all the conductors are same radius. That's why in this case GMR of group A and group B are what? Same. But it is not for all the thing, all problems. Anyway, I'm going to solve for both. GMR of group A, fourth root. What is D11? R dash. into what is D13? 1 to 3 distance 0.2. I'm doing in meters only. This is 2 terms I done. Again what? 2 more terms. D31 0.2. 0.01 into what? 0.7788. 0.7788 times 0.0. Better to write like this so that you will not have a confusion later. Okay, 0.01 here. Please note. Okay. Chalo, anyway, there is 0.01. Okay. Now tell me, what is this? Zero 0.0394 meters. You try GMR group D. Here we get same. Because D within the group na D2 to D24. D4 to D44. You're going to get same again. But not always. Again, I'm saying don't be in trap. Don't be in trap by saying this question. Just like GMD group A, group B same, GMR group A, group B same. In this case, it is same because there exists a symmetry between group A and group B. In that case, okay. What about GMR equivalent? Let me write here. But this is for inductance calculation, not for capacitance calculation. If it is a capacitance calculation, what makes the difference? Tell me here. This 0.7788 will not come. Okay. So that I am going to do separately. Okay. Now tell me what is the next slide I will go. This is 2.005. 2.005. Yes. And this is what? 0.0394. Okay. Yes, 0.0394. If that is the case, tell me what is inductance of single phase line? 0.2 ln millihenry per kilometer, because I am not taken 2 into 10 power minus 7. If that is the case, 0.2 ln 2.005 by 0.0394. So what is the answer? We get approximately 0.785. Okay, L circuit means 2 times of that. It's not a big deal. Anybody can solve this. But what about capacitance? For capacitance calculation, what about GMR of group A? GMR of group A means what? Yes, D1, sorry, D, oh, let's see. Actually, conductor 1, D11, D1, sorry, D11, D13, yes, D31, D33. This is same, but substitution is different. D11, D13, D31, D33. Again, fourth rule. But what I'm going to substitute? D11, R. R is what? 0.01. D13, 0.2. Same. 0.2 into 0.01. Okay. Now, if that is the case, what is the answer? Zero 0.0447. Now GMR of group B also same. Directly GMR equivalent also same. I'm writing here. You can try it. Same. Okay. Clear? If that is the case, what is capacitance of CAN? 2 pi epsilon naught ln GMD. Now you substitute and tell me the answer. First of all, ln of what? 2.005. 0.0. Ln of answer after that. I got 41.64. Just check it. So, and CAB means what? Off of that. Okay. So clear? Clear? Any doubts here? Okay, so I'll give a short break, 10 minutes break. Okay, so after that, again we'll start. Only 10 minutes, not more than that. Okay, after 10 minutes we'll meet. Okay, then I will continue till what? 1:30. Then I'll take a short break for lunch also, not long break, very short break for lunch. Then we'll continue. Okay, so right, so maybe by 3 or 4 we can finish PS1. Then after that, what we'll start PS2. Okay, clear? Nothing great in PS1. Once after line parameter calculation, performance also there, and I will tell you what are the things to be focused in performance of transmission line. Okay. Yeah, I've explained bundle conductors also. No need to worry. Okay. Let's go for a short break. Okay, guys, we'll start the session. We'll resume the session now. Okay, now we'll go for what? Three-phase transmission line. How you calculate the inductance and what capacitance? Directly three-phase transmission line means what? So we have a, the horizontal configuration, vertical configuration, etc., etc. Okay, we're going to see that now. Okay, fine. Yes. Okay. Is my voice is clear, right? It's audible, right? Okay, when it comes to three-phase transmission line, again, three-phase transmission line means what? We have a different configuration. So, unsymmetrical spacing. Unsymmetrical spacing. Three conductors, A, B, C. Okay. Conductor A carries a current of what? I at an angle 0. Conductor B carries a current of B, I at an angle minus 120. Conductor C carries a current of what? I at an angle plus 120. So again, I'm saying these three conductors are what? Belongs to three different groups. Yes or not? Group A, Group B, Group C. Each group consists of only one conductor. That's why no need to go with what? GMD and GMR. Directly, I'm giving the formulas. Please notice this. Okay. So conductor A to B distance, B to C distance, C to A distance. I'm saying X, Y, Z. Since X not equal to Y not equal to what? Z. Okay. Radius of all the conductors are same. That is what R. With this, what is the inductance per phase? Inductance per phase. Again, I'm saying L average. Directly, I'm writing LA plus LB plus LC by what? 3. With that, I can write 2 into 10 power minus 7 ln of cube root of xyz by what? R dash. Remember this formula. Henry per meter. If you want millihenry per kilometer, you write what? 0.2 into ln of what? 2 into ln of cube root of xyz by R dash. Okay. Now, what about the capacitance per phase? Capacitance per phase means what? Yes, 2 pi epsilon naught ln of what? Cube root of xyz. But instead of R dash, it will be R per meter. Now this is for what? Unsymmetrical spacing. Here the conductors are what? Arranged such that A to B, B to C, C to A distance is what? Not same. Generally, this is not a common configuration in practical system. But if you really notice, calculate LA, LB, LC separately. If it is an untransposed line, generally there is a transposed line and untransposed line. Yes, we do the transposition to get the what? Equal inductance of A and B and C. Okay, clear? So if it is an untransposed line means what? LA, LB, LC are not same, but still inductance per phase is what? Same formula we get. I'm going to explain that at the end. Okay, chalo. So next one, symmetrical spacing. Second one. If it is a symmetrical spacing, number 2. Symmetrical spacing, also called equilateral spacing. Yes, please notice that. Symmetrical spacing, also called equilateral spacing, because the conductors are arranged to form an equilateral triangle here. What is the meaning? Conductor A to B, B to C, C to A distance is same. That is what the meaning of equilateral triangle, right? All the sides are what? Equal. So equilateral spacing. Equilateral spacing. Okay. So conductor A to B distance, B to C distance, C to A distance is what? Same. That is, I am assuming D, A, B, C. X equal to Y equal to Z equal to D. If that is the case, you don't need to remember anything. So you can substitute that directly. What is that? So inductance per phase is what now? 2 into 10 power minus 7 ln what? V by R dash. Okay? Because X equal to Y equal to Z, na? That's fine. Capacitance per phase. Now, but practically we are using either horizontal spacing and what vertical spacing. This is a common configuration we use in power system: horizontal spacing and what vertical spacing. Okay, clear. Number 3, I can write horizontal spacing and vertical spacing. Okay, so this is horizontal spacing. This is what vertical spacing. X equal to Y equal to D here. Again, so what I get now? That is what cube root of x by z. If you substitute that, we get inductance per phase 2 power 1 by 3. Cube root, na? Cube root of 2 will be there, but d cube whole power 1 by 3 will get cancelled. Directly I am writing. Please notice that. So capacitance per phase is what? Okay, so this is enough, and we have a double circuit line. I'm not going into that, it's not important. Till now, there is no question on double circuit line in the gate history. This much is enough. But extra is what? What is the charging current? Charging current means what? Charging current of a three-phase transmission line is what? Yes, let me write the formula for charging current. This is valid for three-phase transmission line. V phase omega capacitance per phase ampere per meter. Phase voltage only you have to substitute. Okay, nothing else. Clear? Understand? Let's try one question. Okay, right. So what is the untransposed and transposed line? This is untransposed line. Conductors are arranged at what? Same location. Transposed means what? We do the what? Exchanging of positions. Okay, exchanging of positions. A conductor will go like this. A conductor will occupy A phase position, B phase position, C phase position. B conductor occupies A phase, B phase position, C phase position, and what? A phase position. C conductor occupies A phase position. Sorry, C phase position, A phase position, and what is B phase position? Between what? Sending end and receiving end. But something like this. It's not like randomly we do this. Every one third of the distance, because total length is what? L and L if you take it. Then this is what? Transposition. Practically all the lines are transposed. Because of transposition, remember one thing, communication interference will nullify, but inductance per phase will remain same. Inductance per phase without transposition, with transposition will same. But what is the need for transposition is, yes, to reduce the communication interference or to nullify the communication interference, you may say, and to get the equal inductance for all phases. If you have not done the transposition, na, LA, LB, LC not same. In this case, LA not equal to LB not equal to what? LC. I'm talking about what? Unsymmetrical spacing, especially. For unsymmetrical spacing, LA not equal to LB not equal to what? LC. But this is what? Transposed case, we get LA equal to LB equal to what? LC. But inductance per phase here is what? X. For example, what about the inductance per phase here? Same X only we get. So, because of transposition, average inductance or inductance per phase will not change. Please notice that. Okay. Except that everything fine. Okay. Clear. There are other things also there, but this much is enough. Why we do the transposition? Not to reduce the inductance. Inductance per phase, average inductance will remain same if you do the transposition or not do the transposition. But for unsymmetrical spacing, LA not equal to LB not equal to LC. If you have not done the transposition, to get the same inductances, we are going to do what? Transposition. The other advantage of transposition is communication interference will be nullified. But both symmetrical and unsymmetrical spacing, communication interference is nullified after transposition only. But before transposition, it might be symmetrical spacing, it might be unsymmetrical spacing. There exists a transposition. If we do the transposition, communication interference will be nullified for both unsymmetrical and what? Symmetrical spacing. Again, I'm saying communication interference will be there for both symmetrical and unsymmetrical spacing if you are not done transposition. If we do transposition, nullified. But LA not equal to LB not equal to LC if you not do the transposition for unsymmetrical spacing, but not for what? Symmetrical spacing. Symmetrical spacing, if you do transposition, if you not do transposition, LA equal to LB equal to LC, because the conductors are arranged to form an equilateral triangle, because A to B distance, B to C distance, C to A distance is what? Same. Clear? 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 Okay, chalo. So, that's it. So, after doing the transposition, what happens? Communication interference will nullify for both symmetrical and unsymmetrical spacing. And after doing a transposition, for unsymmetrical spacing, inductances become equal. But average inductance or inductance per phase will remain same. Okay, please notice that. Chalo. So, what is the calling of transposition means? Shifting of positions. We do the shifting of positions for every 1/3 of length. Every 1/3 of length. So, that's it. That's it. Now, next, bundle conductors. Yes, every phase having more than one conductor means what? That is called bundle conductors. So, please notice quickly, I'm going to explain what is bundle conductors, what is the use. Bundle conductors are mainly used to reduce what? Corona. Bundle conductors increase the GMR. Bundle conductors reduce the corona. How? Corona is because of what? Gradient at the surface of the conductor. Corona means gradient at the surface of the conductor, directly proportional to voltage, inversely proportional to what? GMR. If this gradient at the surface of the conductor greater than 21.1 kV per centimeter, then air surrounded by the conductor will break down. That is nothing but what? Corona. Corona happens now. If gradient is less than 21.1 kV per centimeter, there is no corona. Because air surrounded by the conductor will not break down. Air will not ionize. There is no free electrons are produced in the free air. Surrounded by the conductor, there is air that will become what? Ionize. Ionization means what? There is n number of electrons got produced in the air. That electrons are moving in the air with high velocity. For movement of those electrons in the air with high velocity, energy is required. That energy is coming from the conductor. Nothing but corona loss. Some energy, energy indirectly what? Generator to, load it is going. But some energy is going in the form of what? Movement of free electrons in the free air with high velocity. So that is indirectly corona loss. So corona loss is very dangerous value. In fact, you are not taken care. So if you want to take care, you have to reduce the G. If you are decreasing the G means indirectly you are reducing the corona. If G increases, corona will increase. If G decreases, corona decreases. How to decrease the G? By increasing the GMR. Don't see the voltage. Voltage means there. It's a 11 kV line, 11 kV. 220 kV line, 220 kV. 400 kV line, 400 kV. I'm not going to reduce the voltage. But next, what is the other option? GMR you can increase. How you increase the GMR? Instead of using one conductor per phase, more than one conductor you use it. For example, if you have two conductors in the bundle, every phase two conductor, A phase, B phase, C phase. Now tell me, one conductor means what? One conductor means what? Let's say this is A phase only. This is also A phase. One conductor means what is the GMR? R dash. Two conductors means what? There is some distance here between them, small d, if you assume. What is the GMR now? What is GMR now? Square root of R dash into D. Try it. D11, D12. D21, D22. Yes, you have to do it. Then you get what? Square root of R dash into D. So definitely D is very, very high. D is called what? Bundle spacing. Subconductor spacing. subconductor spacing. Distance between the adjacent subconductors in the bundle is called what? D. That is approximately 20 to 40 centimeter, whereas the radius of the conductor is not more than 5 centimeter. Radius of the conductor is not more than 5 or 10 centimeter, but spacing between the conductors within the group, within the safe A phase, one conductor to other conductor distance is what now? Which is what approximately, so 20 to 40 centimeters. If that is the case, definitely what? GMR is high. So GMR increases means what? Gradient at the surface of the conductor will decrease. That is the reason why we are using bundle conductors. GMR increasing, gradient at the surface of the conductor decreasing, then what? Corona decreases. So that's why for 220 kV and above, I told you already, okay, in the morning, 220 kV and above, the line design is based on corona, because 220 kV onwards, corona will come. To reduce the corona, size of the conductor you increase. Otherwise, size of the conductor increasing means cost will increase. Otherwise, go for what? Bundle conductors. Instead of using one conductor per phase, use what? More than one conductor. Okay. For example, let's say there is a single conductor configuration carrying a current of what? I. Radius is R. Now you are converted to what? Bundle conductors with what? 3 subconductors in the bundle. Okay, otherwise 4 subconductor in the bundle, otherwise 5 subconductors, 6 subconductors in the bundle. Somehow they are arranged. Not like this, they are arranged to form a circle here. Okay. Chalo. A single conductor configuration converted to form what? Subconductors, something like this. They are arranged to form what? Circle. N 1, 2, 3, 4. Up to some N conductors here. So again, the total current carrying capacity is I. If that is the case, what is the relation here? Each conductor having a radius of what now? RB. All the conductors are having same radius. What is the relation here? RB equal to R by root N. Remember this also, it's very important. A single conductor configuration is converted to form bundle conductor configuration. But how many subconductors in the bundle? How many subconductors in the bundle? N. N subconductor. N may be 2, 4, 5, 6, 7, 8, something like that. So this is generalized formula. Radius of each subconductor in the bundle for same current carrying capacity. The high I here. RB equal to R by root N. I hope this is clear. Right? A single conductor configuration is converted to form a bundle conductor configuration without changing the current carrying capacity. Then radius of each subconductor in the bundle is RB, that is equal to what? Radius of single conductor configuration divided with what? Root N. Root N, where N is the number of subconductors in the bundle. Remember this, it's very, very important. Okay, now I'm going to write a generalized formula. N subconductors in the bundle, what is the GMR? N into R dash into A power N minus 1. Okay, what is A here? D by. Remember this formula, that's it, don't ask. Where A is the bundle radius. Since there are N number of subconductors, no? N number of subconductors, they are forming what? A circle. So here one conductor, here one conductor, here one conductor, and so N number of subconductors. Where D is what? Distance between any two subconductors. So what is the relation between A and D means what? A equal to D by 2 sine pi by N. Okay, clear? Now this is the GMR, direct single generalized formula. Okay, so if number of subconductors increases, GMR increases. So if GMR increases, there are some added advantages. Inductance decrease, capacitance increase. Inductance decreases, reactance decrease, voltage drop decrease, reactive power consumed by the line will decrease, surge impedance will decrease, surge impedance loading will increase. All these are advantages. Stability increases, maximum power transfer capacity of the line will increase. Added advantages. But is that the reason why we are going for bundle conductors? No. The main reason for going of bundle conductors is what? To reduce the corona. That's it. Nothing else. Okay. So that's about bundle conductors. I'm not going much details of bundle conductor. This much is enough for gate point. Believe me. Now, so the next important thing is that Yes, we'll solve some questions which were asked in gate. Okay, just give me a moment, please. Just give me a moment. Okay. So just hold on, please. Okay. Okay, fine. Yeah, all right now. Just you got the file now. So there is a question here. Hmm, sorry. So so this is a one gate question. I think you can see this question. Where is the zoom option? Right, right, right. Able to see this question? Question number 47. This question. Okay. How to write? I'll do one thing. All right. Okay. Let's try this question. Okay. Right. Consider an overhead transmission line. Three-phase 50H balanced system with conductors located with vertices of an equilateral triangle. The resistance of the conductors are neglected. The geometric mean radius of each conductor is given. Here directly GMR is given. Please notice that. GMR itself is given 0.001. Now you just try this question quickly. GMR itself is given in the question. Just try this. Just try this. Okay. So now, what is GMR? Given 0.01. What is GMD means what? Cube root of XYZ. All the conductors are having what? Same distance. Directly I can calculate. Neglecting the effect of ground, the magnitude of positive sequence reactance. See, don't confuse here. Positive sequence reactance means what? So it's a normal reactance. What is the reactance? How to calculate? Very simple. Reactance means 2 pi FL. Okay. But is asking in ohms per kilometers. Careful. Ohms per kilometer we need to calculate. Okay, we do that. But what is the inductance? Inductance means what? Inductance per phase only. Inductance means inductance per phase. 0.2 ln d by what? R dash. Millihenry per watt kilometer. Okay. But we have to substitute here Henry per kilometer. Then only you will get what? Answer is in ohms per kilometer. Okay. Positive sequence reactance and normal reactance is always same. Okay. Just to create confusion, he has given positive sequence reactance. Okay. What is this? 0.2 ln. What is D? 1 meter, right? DAB, DBC, 1 meter. The geometric mean radius means what? Directly R dash itself is given. That is what GMR. R dash itself is given 0.01. Now you should not multiply 0.7788. You end up with wrong answer. Because it's clearly mentioned GMR value itself. What is GMR value given? 0.01. It's not R, it is R dash given. Okay. So what is GMR given? 0.01. So let's calculate this. 0.2 ln 100 now. Okay. 0.921 millihenry per kilometers. But I need Henry per kilometer. 0.921 into what? 10 power minus 3 Henry per kilometer. So this you have to substitute here. So that you will get the answer for X. 2 pi into 50 into 0.921 into 10 power minus 3 Henry per kilometer. If you substitute, then only you get what? Ohms per kilometer. Okay. Now tell me what is this? .289 is the answer. Just have a look of this. If you want, you can take a screenshot of this. Okay. There's a one question given in what? GATE exam. Based on what? Three-phase transmission line. That's it. So we'll make it fast. So there is another question. Okay, there are two questions. This is very simple. You can try it. Okay. There's a single phase transmission line. Let's see. Capacitance to ground per kilometer is asking. Capacitance to ground per kilometer is asking. Okay. Anyway, we'll solve this question. Very simple. Not the pen here, no. Let's see. The horizontally placed conductors of a single phase transmission line. Single phase transmission line means what? Two conductors. Horizontally placed. Okay, let it be horizontally or vertically placed, not a problem. Having outside diameter of 1.6 centimeters. Okay. The diameter is what here? 1.6 centimeter. Diameter given. So radius is what now? 1.6 divided with what? 2. 0.8 centimeter. Again what? Some people will confuse between radius and diameter. Because in flow, they know radius is what? Half of the diameter. But in flow, they will directly substitute radius as 1.6. Okay. And conductors to conductor distance 6 meters given. 0.8 centimeters means what? 0.008 meters. Yes or not? Divided with 100. 0.008. Okay. And then what? Capacitance to ground per kilometer of each line is. Okay, no problem. Capacitance to ground means what he is asking CAN. 2 pi epsilon naught ln d by r. Farad per meter, but he is asking per kilometer. Let me tell you how to solve this. 2 pi into 8.854 into 10 power minus 12. Na? You take it 10 power minus 9 here. Instead of 12, you take it what? 9. So one more 10 power minus 3 is there. How to write that? Anyway, let's complete this first. Now tell me, this is what? Farad per meter. Instead of that, I will write what? Farad per kilometer. Because 10 power minus 3, I will bring it to denominator. 10 power 3 meters. That is what? 10 power minus 9. Now tell me what you get. You can solve this. 2 pi into 8.854 divided with ln of, tell me what is this? 6 by, and diameter is given 1.6. Once again you check it. 0.008. I got 8.4. Very simple question. Very simple question. If you want, you can take a screenshot of this. Done. Not 10 power minus 12. Yes, that is a common mistake done by the people. Winter child. 10 power minus 9. Because farad per kilometer. So you need to give the answer is in per kilometer. Per kilometer is 8.4 into 10 power minus 9 farads. Yes. Chalo, we'll move on to the one more question here quickly. Now you try this question. A composite conductor consists of 3 conductors of radius r, and he is asking what GMR. The overall GMR is what? KR. Then the value of K is 3 conductors. It's not 3-phase system. All the 3 conductors are what? Belongs to what? Same phase. Yes or not? Okay. If I want to take this, yes. Just give me a moment. So conductor 1, let's say, this is conductor 2, conductor 3. All the 3 conductors are belongs to what? Same group. Composite conductor means what? All these 3 conductors are belong to same group. Radius of R conductor, each conductor is what? R now. Now the distance from here to here is 3R. So he is mentioned indirectly. Simple mass is asking here. 60 degree, 60 degree means what? You know, in a triangle, 60 degrees. This is an equilateral triangle. If this is 3R, this is also 3R, this is also 3R. So you will get total 9 terms. But with respect to 1, with respect to 2, with respect to 3, you are going to get same terms. Then you write what symbol? If there exists a symmetry, then D11, D12, D13 is enough. No need to write. This is also okay. You can write D21, D22, D23, D31, D32, D33. Total how many terms? 9 terms. So that's why ninth root. All are multiplied. Don't confuse. All are multiplied. All these 9 terms are what get multiplied. Now tell me, what do you get? D11 R dash. R dash means what? 0.7788. 88 times capital R. D12 3R. D13 3R. Now you write D21 3R. D22 same. D23 same. So instead of writing ninth root, what I'm saying is this term, this term, this term is what same. Okay, this is always you need to follow. This is okay. You may say shortcut. Why? Because see, with respect to conductor 1, whatever the terms you are getting, with respect to conductor 2, whatever the terms you are getting, with respect to conductor 3, whatever the terms you are getting, then what? I can write only with respect to conductor 1, instead of writing ninth root, I can write what? Cube root. Otherwise, okay, after writing this will be what? Same. This is x, you assume x cube whole power 1, whole power 1 by 9, x power 1, x power 1 by 3. Yes or not? So that's why what? Cube root. Okay, nothing wrong. So what do you get now? Cube root of 0.7788 into 3 into 3. This is r cube. R is there, R is there, R is there. R cube whole power 1 by 3. Simply R. So indirectly, this is nothing but our k. That is what is asking in the question. What is the value of k now? K equal to. Now just calculate that. Cube root of 0.7788 into 3 into 3 into 3 into 3 whole power 1 by 3. Again, don't do square root. Again, common mistake done by the people here, that 1.9137 is the answer for K. Okay, 1.9137 is the answer for K. Just have a look. Is that clear? So this is also a question given. Okay, you want to take a screenshot of this. Next, we'll move on to the next question quickly. Yes. I missed one question. That is here. Yeah, this is the question. A bit typical question, but this is also very simple. You try this question. A single phase transmission line has two conductors of each of 10 mm radius. Okay, 10 mm radius. These are fixed at center to center distance of 1 meter in horizontal plane. That is the first statement, which talks about what? Single phase transmission line. Yes or not? Clear. Single phase transmission line has two conductors. What is the distance between them? 1 meter. Radius of these two conductors are what? 10 mm. Okay, clear. Now this is now converted to a three-phase transmission line. Okay, by adding one more conductor, but at an equal distance from the two single-phase conductors. Okay, try. Then, oh, Sorry, we lost the power. Oh, that's why I'm saying. So even I didn't save this file. That's why I'm saying PDF sharing is not possible. Whatever I written before that, I think it is gone. Anyway, be online. We'll start soon. All the power got restored. Okay, power is back. We'll continue. Just one question we'll discuss, then we'll move on to that. The next topic with a short lunch break. Okay, so yeah, we'll go to the same question. So this is what a single phase line where radius is what 0.01 meters. Now the spacing between them is what 1 meter here. This distance is what 1 meter. I'm assuming this x equal to what 1 meter. Now what is mentioned? So there is a third conductor is introduced. Okay, for the single phase line, when three phase line is fully transferred, the positive sequence inductance per phase of a three phase system is 5% more than of per conductor of the single phase system. What is the per conductor inductance? Single phase transmission line inductance. L single phase I can write now 0.2 ln d by r dash. What is d? That is x. R dash means what? 0.7788 into what? This is. Now what happened? This is converted to a three phase system by introducing a third conductor with same, but this is d, this is d. What is this? X. Let's assume that. Tell me what is GMD now? Cube root of x into d into d. X is anyway 1 meter, so that's why cube root of what? D square. Okay. Now tell me the inductance. What is mentioned? The three phase line is fully transferred. The positive sequence inductance means what? Normal inductance. What is that? 5% is more than that of what? Inductance per phase. This is for three phase. Is what? 5% more means what? 1.05 times what? L single phase. If that is the case, what is the value of D is asking. So I can write here 0.2 ln cube root of D square by what? Same 0.7788 into 0.01. Third conductor also having same radius. 1.05 times 1.05 times same 0.2 ln 1 by. Now let's calculate the value of D. We'll get the answer for D now. You try it and tell me the value of D. Okay, this is another question which is given. Yes, the answer is 1.439 meters. By default, it is in meters only. So that's it. This is another question. Okay, clear. Just take a screenshot if you want. Then we'll proceed. Yes, nothing great. All the questions are very simple after this. This is how the questions are given, from this topic. Yes. Yeah, the remaining questions are 1 mark questions. This is also another question. You can solve this. It's given 10 km long single phase transmission line, but final answer is in what? Millihenry. Let's calculate it millihenry per kilometer. After calculating millihenry per kilometer, you need to multiply it with what? 10 kilometers. Then only you get the answer is in what? Millihenries. Okay, clear. This is another question. You notice this question number 12. That is also given for 2 marks. And you can solve that question. Not a big deal. That's it. Nothing great. And there is a 22 question. This is what? Calculation of GMR. You try this question. Okay. This also you take a screenshot and try this. So gate 22, 50th question. That also you try. Okay. That's it. Nothing great. So the great questions are very, very simple from what? Line parameter calculation. So that's it. Okay. So we will take a 15 minutes break for lunch. Then we'll start again. Okay. Just 15 minutes. We'll start again. Okay. Clear, sir. So that's it. I'll be back in 15 minutes. Okay.